Up to this point, we have defined the nth Maclaurin polynomial to be this polynomial. And this polynomial we know approximates f at points around x equals 0. Now what we can do is take this pattern and extend it to infinity. In other words, create an infinite series out of this pattern. And this series will then have a sum of equal f as long as the infinite series converges. And the convergence of this series, because it's a series involving x where x can vary, will depend on the values of x. So the Maclaurin polynomial has a finite number of terms, n terms. The Maclaurin series just takes that pattern to infinity. And so the Maclaurin polynomial can be thought of as the nth partial sum of the series. The polynomial is the partial sum of the corresponding series. So let's just make this a little clearer in terms of a specific example. We've already shown that our Maclaurin polynomial for sine x around x equals 0 is, in other words, sine x is approximately this polynomial. Remember, we're starting with n equals 0. Our Maclaurin series, therefore, for sine x would be this polynomial taken to infinity, which, if we write that in sigma notation, is this. So we're saying that sine x is exactly this, but here's the important part on the interval of convergence. And by interval of convergence, we mean the values of x for which the series converges. You'll notice that this infinite series is not a series of constants, and so the convergence of this series will depend on the values of x. So we're saying that this series is equal to sine x on the values of x where the series converges. Now, how are we going to find out where the series converges? Well, remember that we know that a series converges if this limit is less than 1. Remember that this is the ratio test for absolute convergence. So if we can find the values of x for which this limit is less than 1, we have then found the values of x on which the infinite series converges. So let's apply this to sine x. Y equals sine x converges to our Maclaurin series this is our a sub k if the limit as k goes to infinity of the k plus first term over the kth term, absolute value of that is less than 1. So applying that to my series, I can leave the negative 1 to the k out because that's going to be the positive negative back and forth. I need to continue to put the absolute value in because remember x can be any real value, which can be positive or negative. So this is not necessarily a series of positive terms even if I ignore the negative 1 to the k. So I need to do absolute value of the k plus first term and that limit needs to be less than 1. So rewriting and simplifying. That's the top fraction there, divided by the bottom, which I can multiply by the reciprocal. And on this I can subtract the exponents, which is going to give me x squared in the numerator. And I can reduce a factor of 2k plus 1 factorial numerator and denominator, which leaves me with this on the denominator, and that's got to be less than 1. If I then do my limit, the 3 and the 2 here will not be important, and so I'm going to have 4k squared, x squared over 4k squared as k goes to infinity. That's going to mean that this limit is 0. And 0 being less than 1 means that my series converges for all values of x. Therefore, we're saying that sine x is equal to this Maclaurin series when the series converges, and we've shown that the series converges for all values of x. So my interval of convergence is x is all real numbers. Similarly, you can take any Maclaurin polynomial, take it to infinity to create a Maclaurin series, but remember that when you're dealing with an infinite series, you need to find the interval, the values of x for which the infinite series will converge. And you can do this with Taylor series as well. Since a Taylor series is the same as a Maclaurin series, it's just that you're centered around x equals a. Here's your Taylor polynomial of n terms. If you take it to infinity, you then have a Taylor series. This is your approximation for f around x equals a. This is what f equals on the interval where the series converges. And just like with Maclaurin, the nth Taylor polynomial can be thought of as the nth partial sum of the Taylor series. And the Maclaurin and Taylor series are both examples of what we call power series, which we'll talk about in the next video.